All right. Now we're going to continue with Dmytro Khimchenko, and he's going to be presenting Ethereum Vulnerability Detectors. He's an Ethereum security auditor at TUM Blockchain, and he has a background in penetration testing. So, applause for Dmytro.
Hello everyone, I'm really excited to be here to present this topic. My name is Dmytro Khimchenko. I'm working as Ethereum auditor at TUM Blockchain Security. And now I want to talk with you about static analysis. Static analysis nowadays is a really hot topic, and plenty of companies contribute to that. For example, Bits contribute to Solidity, Siphon contributes to Adrin, and our TUM Blockchain Security contributes to Wake framework. So, what is static analysis? It is process of reasoning about the code without running it. Where we can use it? We can use it for optimizing the code by the compiler, so it saves gas for us, and also it saves gas for the deployment. Of course, we can use static analysis for finding issues and bugs in the code at the early stage. And of course, we can do coding support for our developers to make their mental health better. Also, I want to define detector. It's a program that uses static analysis to detect issues. Okay, let's speak a little bit about Wake framework. Wake framework, it's open source tool that we use for development and testing of Solidity smart contracts. We have written it in Python. We have on-chain and on-dev chain contract interaction and contract testing. And also one key feature that we have, it is fast testing in Python. Not in Solidity, but in Python. So we have better differential fast testing analysis. And also, a colleague of mine, Joseph, will have talk at around 16 hours about fast testing. So you're welcome there. Also, we provide language server support via Virtual Studio Code. So you can download extension there, and it helps you to develop the code and also detect issues at the early stage of the project. Also, we have static analysis framework built in there, and of course we have built-in detectors and printers, which really help to think about code and how the project works. And what is wonderful is that we are providing API for building custom detectors. So you can develop your own detector or printer, and you can contribute to Ethereum security by your own detector. Okay, let's speak about workflow of static analysis. Firstly, we use Sol, a compiler, to create abstract syntax tree. However, this abstract syntax tree has really small data about code base. And we need to enrich it with connections, with type of connections, with type of nodes that are introduced in abstract syntax tree. And we do it by enriching it with, as we call it, intermediate representation model of the tree. And after that, we can do semantic analysis. It includes type checking, it includes data flow analysis, and it includes config flow analysis. Let me speak a little bit more about this intermediate representation model in IST. First of all, we fix abstract syntax tree bugs. After that, we identify every node in our abstract syntax tree with unique identifier for better analysis. And of course, we enriching these nodes and edges with extra types to better analyze it and looking into deeply into a core base of smart contracts. Also, I want to mention that one abstract syntax tree node type equals to one intermediate representation node type. Okay, but how the hell it looks like? This how we can think about intermediate representation model. Yeah, it's a huge amount of data, but let me go through it. It's a source unit that has every smart contract. This is contract definition. So, or we can also, in another graph, you can also find information about inheritance contracts and so on. After that, contract definition has, as a children, function definitions. Function definitions has a parameter list, one parameter list that is responsible for parameters that are put in function, and another parameter list is responsible for return values. And of course, function definition has as a child block that contains all other statements. So if statement, return statement, some binary operation type. Also, we have types of this binary operation identifier that identifies as a variable, and the literal is some constant value. Okay, but what we can do with this huge amount of data? We have special functionality to analyze it. First of all, we have visitors pattern that lets us to grab this node, specific node type, to analyze it. Here we have a function definition. So what this function does? It grabs this node for future analyzing. And it has as attributes all of these children and all of these parents. It's like really simple usage of this visitor function for grabbing specific node types. Also, we have control flow graphs. I guess you're familiar with it because it represents all of the paths that function has, and we create for every function one control flow graph in smart contracts for better analyzing. And of course, we have data dependency graph. Data dependency graph we create for every variable, and we can see which value are assigned to it and where is this variable is used. Okay, this is staged. Let's go to the right after right detector. Actually, we found it useful to analyze it because in our project we have found that in code base there are some right after right issues, and we thought about it. Okay, that can be automated, and everything that can be automated must be automated. So we decided to create a right after right detector. Yeah, I guess you're familiar with it. It's analyzing of the variable. First of all, when the issue occurs. When the value is assigned to the variable, it is not used. And after that, another variable is assigned to it. And here, in this function, can be critical vulnerability. Why? Because because the return value to the external code is not checked, and it is really can be an issue. So we decided to create a detector. Let me go through let me go through an overview how this detection works. Okay, we take first write operation. in the control flow graph, we go through all of the paths that function can go, and if there is no usage in all paths, we report it as an issue. In other words, if at least one usage at all control flow graph exists, we don't report it. For more detailed description of the algorithm, you can go after me. I have a poster for this presentation where this algorithm is extended. So I can go through all of the control flow and the dependency graph interactions. What challenges we met during implementation? First of all, we also learned how to analyze function arguments and how to analyze function modifiers. Also, during this implementation, we found issue in wake framework with representation of shortcuts, where shortcuts was not considered as a read operation from the variable. What challenges we didn't solve yet, and this will be our future work, it's state variables. We now don't analyze it because we cannot analyze it precisely, and in this detector we really want to identify issue with 100 precision. And also, for now, problem with assignments in the loop is not solved, and it will be our future work. Okay, when we implement a detector, we want to evaluate it somehow. And what is the best way to evaluate it than to compare it with other implemented detector in another framework? So we took Slither implementation of write after write detector, and we run on the same dataset, on dataset of almost 9,500 contracts, and we extracted results after run of Slither. Because of not enough time, we didn't analyze all of this 9,388 contracts because it's like infeasible manually to go through. So we have chosen randomly 50 contracts for deeply analyzation. So we go through 50 contracts there. And also, we found out that our wake detector find more issues than Slither, and we decided, okay, what issues Slither found? And we want to see them, and we want to evaluate them, so we will know where should we work and where should we improve. First experiment with 50 random chosen smart contracts. We have 100% precision in comparison with Slither, and also we have better recall, almost like 95%, and also we have better as a result at one score. So the second experiment, which we did, just to mention number of findings on this big data set. We found 672 issues, where in comparison with Slither, which found just 200. And after we analyzed what issues Slither found, and we didn't, like in wake framework, it's resulted in only 10 true positive, which was about state variables that we haven't implemented yet. And there are like 53 false positives, and it results in precision 16, or almost 16%. Yeah, and our future work, we want to standardize the measurement process of the for the detectors, because in future I hope there will be more detectors to find issues that can be found automatically. And we really want to standardize this process, how to do that, and how to decide if detector is good or bad. And also we want to measure other weight detectors against state-of-art tool like Slita. And that's all from my side. See you around, and thank you for your attention.